Our next presenter is Anna Marshall. She's a second year geosciences student studying fluvial geomorphology. And she knew she wanted to study rivers when, at age 5, she converted her dirt road in northern Maine into a series of dams and canals. She says that she's remained fascinated by the patterns of flowing water to this day. Her presentation title is Rewilding Rivers, Understanding How to Restore Critical Hydrologic Processes in the Face of Climate Change.
Rivers are the veins of the earth. Across the globe, they pump water and sediment out to the ocean, they provide critical habitat, and they transfer solutes and nutrients. Yet rivers are often taken for granted, and their natural value has been historically undermined by humans for millennia. Today, many rivers that we see are no longer natural, in that their water has been diverted, their shape has been straightened, and elements of complexity, such as wood in the river or multiple channels, have been removed. I'm a fluvial geomorphologist, which means I study physical changes to rivers. Specifically, I look at hydrologic processes in rivers with high levels of natural complexity and minimal human modifications in order to understand how we can restore those elements in rewild streams that no longer have as much ecological and physical function. To narrow in even more, I look at processes around wood in rivers. Wood enters rivers via downed trees and erosion processes, and historically, it's something that was abundant in rivers prior to activities like logging and urbanization along river corridors. However, even as work to restore rivers grows today, perceptions of wood in rivers remains largely negative, and wood is something that's seldom incorporated into river management. But in fact, wood in rivers has tremendous value, particularly with a warming climate. Single pieces of wood and log jams can promote transient storage, which is something that essentially acts as a river's liver by slowing down both surface and subsurface flow paths of solutes and nutrients, and cooling water temperature before it returns back to the stream flow. My master's incorporates field and modeling methods to measure those transient storage flow paths around log jams, using salt to trace the paths and understand the relationship between wood and transient storage. My research asks questions about spatial and temporal dynamics of wood in rivers and whether increasing the quantity of wood drives patterns of transient storage. For example, do we see a linear or nonlinear relationship with transient storage as you add more wood, or is there some sort of threshold? This is important because thus far, no one in the scientific community has looked at the additive effects of multiple log jams in a river. And in the case of a natural forest, there's typically going to be more than one piece of wood in a river. To dig deeper into this idea, I've built a physical model of a river, or a flume, to directly manipulate stream flows and wood characteristics. I've added multiple jams from the observed differences. I've changed the style of the channel, I've increased and decreased flow. And looking at the results, stream segments with greater or lesser amounts of wood, I can infer that river management designed to foster transient storage can effectively focus on retaining wood, either by continuing recruitment or fixing engineered log jams into place. These results shed light on one of the persistent challenges that river and floodplain project practitioners face, which is the lack of best available science to draw upon, lines of evidence to support detailed design and construction. My predictive results provide understanding into the value of adding wood into rivers and the scale and quantity at which to do so. In doing so, we can begin to restore complexity back to rivers and allow the veins of the earth to flow freely once again. Thank you.